Welcome students. This is our EDC lab. In this we are going to conduct first experiment as PN junction diode. So in this PN junction diode, the equipment or the apparatus required are, here we have one breadboard. This is first component, and upon which we are going to conduct or construct the circuit diagram. And this is the major element, PN junction diode. This is the physical device of PN junction diode. So which has two leads. One is anode, the other one is cathode. So here we will be having a silver color strip to the right side of this component. This can be considered as cathode, and the opposite side will be considered as anode, which is plus and negative terminals of this diode. And the second component we require for this experiment is resistor. Here I am using 1 kilo ohm resistor. So in this we will be having the color coding as brown, black, black, brown. So if you calculate, you will be getting 1 kilo ohm resistor. This is the other component. And in order to measure the current through the diode, we want digital ammeter, which is ranging from 0 to 200 milliamps. In order to measure the voltage across the diode, we are using another meter called digital voltmeter, which is ranging from 0 to 20 volts. And we have dual regulated power supply ranging from 0 to 30 volts. We are using this device to provide the external voltage. And to connect all the components, we are using the connecting wires. These are the basic components what we want to use for this PN junction diode. Now let me explain the circuit diagram. Now, two biasings. Diode can be connected in forward bias, and diode can also be connected in reverse bias. So forward bias means, already as we have seen, this diode is having positive terminal and negative terminal. Then if positive terminal is connected to the positive terminal of the battery, then negative terminal, if it is connected to the negative terminal of the battery, we can call this biasing as forward bias. Then we are having reverse bias. Simply if we interchange the terminals of this diode, we can get the reverse bias. Okay. So now let me connect to the circuit diagram. This is a circuit diagram. As per this diagram, we are going to connect the components. Let's start the connections. So on this breadboard, we are going to connect the circuit diagram as per the diagram. So in this, first I am taking the diode, and I am, see, this terminal is positive terminal and this silver strip side is negative terminal. So in the breadboard, in this region, on the same line you have to connect the other terminal also, like this. Okay. So on the same line I have connected positive terminal here and negative terminal here. Okay. So these vertical lines will be called single node, but when coming to this horizontal lines, we will be having different nodes. So on the same line you have to connect this diode. Then let us take the current limiting resistor. We can call this as this. We can connect this is any terminal you can connect. Okay, no problem. So let me connect in the same line. See, diode is connected here and to this in series with, because this will protect our diode, okay, from the fluctuations. That's why I am connecting this resistor here. So we are connecting like this. Afterwards we have to measure how much amount of current is flowing through this diode and how much voltage across this diode. So in order to measure that, we have to connect this ammeter in series with diode, and this voltmeter must be connected in shunt with this diode. Okay, let me connect this. So these are positive terminal. This color indicates this is positive terminal and this is negative terminal. And for the voltmeter also we have this is the positive terminal and this is negative terminal. So let us take this ammeter positive terminal and let me connect. Let me connect in the circuit diagram. That is, to this negative terminal I am connecting the positive terminal of this ammeter, and the negative terminal of the ammeter is connected to ground. Negative terminal is connected to the ground and positive terminal is connected to the negative terminal of this diode. Then voltmeter, the voltmeter positive terminal is connected to the positive terminal of the diode, okay, and negative terminal of the voltmeter is connected to the negative terminal of the diode. That means this is in shunt and this ammeter is in series. Voltmeter is in shunt and ammeter is in series with this diode. Then finally we are going to connect this external source, that is DRPS. From this we are going to connect the voltage required. So here also we have this is positive terminal and this is negative terminal. So positive terminal of the DRPS is connected to the resistor, which in turn it is connected to the diode only. Simply it is a protection. Negative terminal is grounded. That's all. These are the connections for the P junction diode. Let us do the experiment. So before that we are making sure that the knobs are at minimum position. Okay, we are switching on. So by varying this applied voltage, this is the external voltage what we are applying. By varying this applied voltage to the diode, we have to measure how much voltage across the diode and how much current is flowing through the diode. So these two meters are used for that purpose. So first let me start, and before that let us have one important point here, that cut-in voltage. Cut-in voltage of the diode is nothing but by varying this supply voltage till certain voltage we are going to get minimum current, so zero current. Okay, so zero current, so we don't get any value here. So that current will be called, or that voltage, particular voltage will be called cut-in voltage, at which current flows through the diode. So depending upon the silicon and germanium materials, the current cut-in voltages will be different. So here I am starting with 0.3. Here I am using 0.3 volts. So for this corresponding 0.34 volts is the current voltage through across the diode, and zero point 0 milliamps as the uh, current through the diode. So before this 0.3 and 4 we are not going to get any current. So till that point I can note down the values like that. So here I am using the serial number, applied voltage in volts, forward current, forward voltage in volts, and forward current in milliamps. So initially for first value 0.01 0.00 we don't get any voltage and we are going to get zero current. For the second one, whenever we are having 0.4 we are getting 0.141 volts and zero point 0.1 as the current. So this particular voltage will be considered as the cut-in voltage for this particular diode. So this voltage will be differ for different types of diodes. That is construction, if the diode is constructed with silicon diode, this value will be different, and if it is germanium it will be different. Okay, so let us take one more value. So by changing this fine tune we can change this value in terms of points. Okay, 0.6 let me take, or 0.6, 0.6, or right. 0.8. For this 0.8 we got 0.5 volts and 0.3 as the current. Similarly, for 1 volt, for 1 volt, for 1 volt we got 0.54 as the diode voltage and we have 0.5 as the forward current. So fourth reading, for 1 applied voltage we got 0.54 and we have 0.5. So in similar way we have to vary different values. Let me take 5 volts. For 10 volts. For 10 volts. Okay. For 10 volts I got 0.7 volts as diode voltage and this is the current 9.2. So sixth reading is for 10 volts I got 0.7 and 9.2. Like that. That means if you observe the readings here, if you are increasing this voltage, applied external voltage, the forward voltage is increasing and at the same time the current is also getting increased. So if we take the characteristic of this diode, then that means we have to take the graph forward current and forward voltage. Let us take along x-axis as forward voltage and let us take the current as along y-axis. So for each values, if we plot this graph, this voltage, forward voltage versus forward current if we take, then for different values we are going to get the graph like this. So this is the voltage at which it is starting, that is 0.4 volts at which current starts. Till this point I can assume the current as 0. So if we go on increasing this, so observe the variation is very little. Variation of this voltage is very little. So that means this current will be getting more for small duration of these voltages. Like this we are going to get the forward characteristic of the PN junction diode. Now let us discuss them or let us do for the reverse bias. Now let us do the reverse diode characteristics. In this simply we are changing the terminals of the diode. So we are till now we have connected positive terminal to the positive terminal of the diode and negative terminal of the external voltage as negative terminal. Now just simply we will interchange the diode terminals or we can change the terminals of this supply also. Anyway we are changing we are connecting the negative terminal to the positive terminal, positive terminal of the external source to the negative terminal and negative terminal is connected to ground. Simply we have interchanged the terminals of this diode. Okay, and as in the reverse bias we are having very small amount of current. So in order to measure that small amount of current we are using microamps digital ammeter so that we can get small current, though we are getting this number as big, but it is in microamp, so it is very little amount of current. Okay, so now let us do the process. So I am switching on, make sure that these knobs are at minimum positions. Okay, then let us vary this voltage and let us measure the voltage and currents. So here the variation of as though even for different values of voltages we will get very less amount of current because you know the theoretical values of this diode. In reverse bias diode is completely blocking or it is not allowing any charge carriers. There is no movement of the charge carriers across the junction, but very small amount of charge carriers will cross the junction, so which is measured in terms of microamps. So let us do. So I am varying the supply voltage. Okay, I am varying the supply voltage to 1 volt. I am getting the voltage as 0.8 volts. Here I am getting 74 microamps. So for the same thing, if we take the readings, serial number, let me take applied voltage, reverse voltage, reverse current. This is in microamps, this is in volts. So for 1 volt, I am getting 0.89 volts as a diode voltage, and the current as 81.5 microamps. Similarly, if I change this to 5 volts, for 5 volts, let us slowly vary the external voltage. So if I vary this to 1.5, I am getting 1.26 as the voltage and 117.9 as the current. So second 1.5 volts and 1.26 and 117.8. So like this, if we are going to change or if we are increasing this external voltage, okay, if we increase this voltage, we are going to get different values. The reverse current also increases, but it is very minor current. So for that, we are noting down for 1.8, we have 1.6 and we have 150. Okay. Similarly, if we change to 2.5, so if I change this to 2.5, I got 2.16. Okay, we got current as 1.57, 157.7. Okay, like this we'll get the readings. So then if we draw the reverse characteristics, so this is reverse voltage and this is reverse current. So for different values of reverse voltages, we are getting different currents. So if for each values, if we draw the curve, we'll get the curve like this. Okay, here observe, this is in microamps and this is in volts. So okay, this is the reverse characteristics of the PN junction diode. Okay, after drawing the graph, so we'll get the graph like this. This is the model graph. So here along y-axis we are taking the forward current. This is forward voltage. This is reverse current. This is reverse voltage. So where we are getting the current will be called cut-in voltage, and at which we are getting the sudden increment in the current, that is called breakdown voltage. These two voltages you have to measure from the experiment. Thank you all.